Hello Linux fans. Today I would like to discuss a little bit about the processes that go on behind the scenes with Linux and how to manage those processes. Any operating system, Linux included, will always have processes that are running beneath the surface. And today I would like to go over some of the Linux processes, how we know what they are and how to control them, and just get a little better understanding about how these processes do what they do under the surface every time we use our computer. First, let's take a look at the objectives of what I would like this video to cover. First of all, I would like to categorize the different types of processes that run on a Linux system. I would like to talk a little bit about viewing the processes using standard Linux utilities, and these could be a little distro specific, but it's more or less common across the distros that are available today. I want to illustrate the differences between common kill signals. That sounds a little harsh, kill, but kill basically means stopping a process for whatever reason you have to stop a process. And I want to describe a little bit about how binary programs and shell scripts are actually executed and how they could become processes in and of themselves. First of all, let's talk about a little bit about Linux processes themselves. And I want to go a little bit into the distinction between a program and a process, because this could be a pretty important distinction. A program, and a lot of you, especially those of you who took programming courses, are probably very similar with different types of programming. They can be done in different, what they call programming languages, beginner's all symbolic instruction code, or good old-fashioned BASIC, as we like to call it, those of us who've been around a while. There's Fortran, there's Watt5, there's C++, there's Pascal, there's a bunch of them. There's also certain types of shell scripting. We do in Linux Bash, but there's also Python and many other types of non-compilable but interpretive scripting programs. But basically, a program is a structured set of commands that's stored in an executable file on a file system. That's a generic definition. Executable form could mean many things, and there could be different types of file systems. Compare that to a process. A process is a program that is running in memory and on the CPU. So what's the difference between a program and a process? Well, that's easy. A process is a program that's actually running, and a program is basically in storage on a file system. In a nutshell, that's the difference. Okay, Linux processes. There's very different types of processes within the Unix operating system. There's what they call user processes. Those are processes that are begun by a user, and that's run on a terminal. It can be a TTY, it could be a terminal in a shell. You can actually, initiate those different ways in the Linux community. But basically, a user process is a process that is initiated by a user. Daemon processes, on the other hand, is a system process that is not associated with a terminal, and it's not associated with any particular user. Instead, it's initiated with the system as a whole. Now, remember, when you're running a GUI, or you're running a command line interface, or whether you're running a graphical user interface, if you're a user, no matter which form you're running, that's considered a terminal. Because remember, in a prior video I mentioned in different distros of Unix, such as Mint, the GUI is associated with TTY7. So that actually is a terminal, even if you're not in a terminal. Running a GUI is associated with the terminal. So that's something to remember. A daemon, on the other hand, is system-wide. Doesn't matter what terminal, if you're on the system, daemon processes apply to you. We identify processes by what's called a process ID, or a PID. Basically, that is a unique identifier assigned to every process as it begins. And as we will see, those can be determined by process numbers. For example, in a lot of Mint distributions, 0, which is always the init process, and daemon processes run up to PID 499. 500 and above are usually reserved for user processes. And with some distros, the cutoff is 1,000. It's basically distro significant where the cutoff is, but the general idea is the same. Okay, Linux processes, I give the example here, and here we see how processes can have a little bit of a tree. This is where the parent-child idea comes in handy. Here is a main process. It's, let's say, process number 1. Okay, its PID could be 134, and its PPID, let's say, would be 56. Process number 2 has a PID of 291. So 291 is process 2's PID. But the PPID, the parent process ID, is 134, as it is up here. Process number 3 is process ID 348, but you notice its PPID, or parent process ID, is exactly the same, 134, because these are both child processes of process number 1, which has a PID of 134. Its parent, not shown in this slide, would be 56. You notice down here, process ID of 291 has 2 children, PIDs of 488 and 571 respectively, but both of them have PPIDs of 291. So that's sort of the idea of how the parent-child concept works. Okay, looking a little bit closer as to what I was talking about earlier, process PID 0 is always going to be what they call the INIT, or the init, initiation daemon. That's the very first process to run in Linux. That's what starts everything else going. It starts a whole bunch of other daemon processes. One of those daemon processes is going to start a user logon. The user logon will then initiate a bash shell. And when you turn on a Linux system, even if you're running the GUI, you will see that it is actually logging you into a bash shell, which the GUI is going to run under. So even if you're running a GUI, it's still running through a TTY or a bash shell. Then you have your user processes down underneath. That's how the process genealogy is laid out. When you want to view process, there are various Linux utilities that you can use to view a Linux process as it is going on. First one we'll talk a little bit about right here is this PS command. The PS command is the most versatile and most common Linux utility that can view processes without any arguments, because like with all Linux commands, you could specify arguments, and that makes a little more specific as to what's going on. The PS command will simply run a list of processes that are running in the current shell. And that can be pretty significant. You're looking at the processes that are running in the current shell. Okay, it'll tell you the state that the process is in. Okay, the current state of the process on the processor. It can be sleeping, it can be zombied, it can be running. We'll get a little bit more into the different states in a minute. But most of the processes we're going to look at are either in the sleeping or the running state. Sleeping is it's sort of not active at the moment, but it's sort of in memory there, ready to go. Running, it's active and it's actually in the processor using CPU cycles and doing what it's supposed to do. Then there's what you call zombie processes. These are what you want to kill a lot of time. You want to kill the zombies, so to speak. And that's a process that's finished executing, but for some reason its parent has not yet released its PID. So the PID is still active and it's still using up resources even though it's not really doing anything anymore. And that's sometimes also known as a defunct process. Okay, there's also different values you could have. The process priority. The process priority is a number assigned to a process, and it's used to determine how many time slices the processor will receive. In other words, is it a high priority process or is it a low priority process? And sort of related to, but sort of opposite of that, would be the nice value. That's a little bit of a hazy concept, but it'll make sense when we explain it in a little bit. The nice value indirectly represents the priority of a process. The higher the value, the lower the priority. Now, this is for the nice value. It's sort of mirrored for this priority number here. But the higher the nice value, the lower its priority. That's important to remember. When you're viewing processes, if you're going to use the PS command, there's certain options, as I mentioned, that you can use, and I'm going to discuss a few of them now. There's the -E option. -E displays all of the processes running on terminals as well as the daemon processes, or the processes that do not run on a terminal. And a good way to remember that, like Linux, because it can be sort of cryptic at times, it's good to have some kind of a mnemonic or a memory jogging way of looking at it. You could look at this -E sort of as everything. It displays all the processes either on a terminal or daemons that are not on a terminal. It'll give you everything. -F displays a full, F for full, list of information about each process, including the UID, the PID, the PPID, or the parent process ID, the CPU utilization, how much of the CPU it's using, the start time, what terminal it's associated with, processor time, and the command name that would call it. So you see, if you use this -F, you're really getting a lot of information. L, as we've seen in other commands, could stand for a long list, L for long list, of information about each process, including the flag state, UID, PID, PPID, CPU utilization again. Only this is going to give you the priority, the nice value, the address, the size, the channel, terminal, and then again the command name. So you see the F and the L are really giving you a lot of information here. If you just use the A, it's going to give you all processes running on terminals. That could sort of be all, but all isn't everything. All is just terminals. And X is going to give you all the processes that do not run on terminals. So you could look at it as E being equal to A plus X. A is terminals, X is not on terminals, E is everything. Good way to look at it. Okay, in viewing processes, there's also a command called the top command. The top command is the most common command used to display processes other than PS. PS being the most common, but top is also very, very common. It's going to actually display in an interactive screen listing the processes organized by processor time. Processes that are the most popular as far as using the most processor time are listed at the top. Processes using the least processor time are listed on the bottom. And as I mentioned, this command is interactive right here, interactive. So then you could actually see processes move up and down as they're using more and more processor time. You could see them disappear. You could see them appear. It's a very nice command to see what's actually going on the minute you're looking at it. You could also see if there's what they call rogue process. Rogue processes are different from zombies, and I want to get a little bit into that. A rogue process is a practice that has become faulty in some way and continues to consume far more system resources than it should. Zombie processes, they're there, but they're not doing a whole lot. Their PID is active. They're using some resources, but not a whole lot. A rogue process can build on itself. It could start eating a lot of machine resources, and it can really be a problem, even to the point sometimes of locking up your system, because they can use up all the resources and not leave anything left for any other processes. So they can really cause a lot of headaches. The top command can be used to change the priority of these processes or any other process, or actually kill them. Okay, if you're talking about the kill processes, which we'll talk a little bit about now, okay, a kill signal is sent to the process from the terminal, from the user or administrator, and a kill signal is a type of a signal that is sent to a process by using the kill command. And there's actually a command called the kill command, and the kill command is used to kill processes. Different kill signals affect processes in different ways, and we will cover that in a chart in a little bit. The kill command that kills all instances of a process by the command name. So you can send a kill command to a particular process that's included in the command name, and that basically will kill whatever process you're referring to, and you specify the kill signal level. And this is sort of a graph of the kill signal levels here. You see there's 1, 2, 3, and then it gets a little hairy. It goes to 15 and 9. And these sort of go up in order of how you kill. In other words, the extreme that you kill. Kill signal number 1, it's also known as the hang-up signal. It'll stop the process and then restart it again with the same PID, but it'll end it and then restart it with the same PID. Kind of rebooting a computer as opposed to shutting it down. And you can edit the configuration file by running a daemon. Okay, the daemon may be sent a signal to restart it when the daemon starts again, and it will read the new configuration. This is used a lot of times if you edit a configuration file while you're using the machine and you want the machine to pick up where it left off, but you want it to use the new configuration. You basically send a kill signal SIGHUP, which is a kill signal number 1, and that'll stop it, restart it. It'll read the new file with the same PID, and it'll continue running your signal. Okay, SIG-init, or kill signal number 2, it sends what they call an interrupt signal to a process. Although this is one of the weakest of the kill signals, it works most of the time. Okay, a lot of you, especially us old timers that used to do a lot of programming in BASIC, we're familiar with the Control-C combination. That's what Control-C is. It's a kill signal 2. And it'll kill a running process. Okay, the SIG-init is actually what's being sent to the process. Okay, SIG-quit. This is used a lot when you need what they call a core dump. Okay, the quit signal terminates the process by taking the process information in memory, saving it to a file on the hard disk in the current working directory. Okay, you could get to that by a Control-/ key combination, and it'll kill the process running, but it'll also dump the memory core. So that's useful if you need information about what's going on, why the process went faulty, what you need to change. So that can be very useful in debugging purposes. Okay, SIG-term, which you could think of as SIG-terminate. Again, I like to think of little memory joggers here. That's a software termination signal that is the most common kill signal used by processes to kill other processes. So this term, it's sort of like a termination for processes to use on each other, so to speak. This is the default process used by the kill command. So if you issue a kill command, but you do not specify a number, it will default to 15. Last, but definitely not least, is the SIG-kill. which is number 9, and that's the absolute kill. That actually forces the Linux kernel itself to stop executing the process by sending the process's resources to a special device file called /dev/null. Remember, in Linux, everything is a file. So if you take all of the resource associated with a process and send it to a null device, right out of the kernel, and you send it to a null device, that's going to absolutely stop it. No way it's going to escape that. If this doesn't do it, you're going to have to do a hard power cycle on your machine. This is as strong a software kill as you can get. Okay, talking a little more. Okay, trapping, the process of ignoring a kill signal, and the kill all command. Okay, the kill all command is the command that kills all the instances of a process by the command name. In Linux, sometimes you can have multiple processes running, and if you kill all, that kills off every instance if you have multiple instances of that command running. Process execution. We'll talk a little bit about that. Okay, there's what they call binary programs. I mentioned those are usually programmed in a higher level language and are compiled, such as C++, Pascal, some of the newer programming languages that you have to write the source code, compile the source code, execute the program, and then hopefully if you don't have any bugs in it, it'll run. Otherwise you have to debug it, recompile it, etc. There's shell scripts, which let's say Bash, Python is a form of shell scripting. This is when you actually write in a terminal like a Bash session. And then shell functions. A lot of shells have built-in functions which are contained in libraries which can be called by programs or scripts, and they can be used in programs or scripts to perform whatever function that they're programmed to do. Forking. Forking is a concept where when you create a new Bash shell child process from a parent. In other words, you have a parent, it creates 2 child processes like we saw earlier in the video. Each child process could then create other child processes. That's called forking. And forking is carried out by what they call the fork function of the Bash shell. And this is an example of that right here. Okay, process forking. You have a Bash shell, process ID 488, parent 142. Okay, this child here is going to be PID 621, but you notice its parent is 448. You could have a wait state here. You could have another child shell here. And again, its parent ID is 142. It's 488 for its PID. Okay, notice here, this is actually the same process here and here, but it goes through this wait state. Okay, here, after the fork here, this goes through the exec command. Let's say you issue the ls command. Both of these could wind up on the exit line. So you kind of have a fork and a wait. So you have a split point here, but you see they both wind up in basically the same place. Going a little further, I want to discuss a little bit about running processes in the background. And this always happens. These are the things you don't see, but our computers could not work without them. You have foreground processes, process for which the Bash shell that executed it must wait for its termination. In other words, if you're running a process, if you have a script that runs multiple processes, you have to run A before B will run. Then B has to finish before C will run. And to give an example for those old timers, before they invented printer queues, in the early days of personal computing, if you printed a document, you had to wait for the first document to finish printing before you could print the second document. Now they have a print queue, everything goes in the queue, and even though you don't see it because it's become more of a background process now, but it's basically the same thing. You submit 10 jobs into the print queue. The print queue then has to wait for job 1 to finish before it could send number 2, wait for 2 to finish before it could send number 3, but instead of being in the foreground where the user waits, now it's in the background. The user sends as many as it wants, and the printer queue waits. So this background process does not require the bash shell to wait for its termination, but it may require something else to wait for termination. Upon execution, the user will receive the bash shell prompt back, or the print queue back and clear. Running process in the background again, okay, there's what they call the jobs command. Okay, the jobs command is a command that you use to see a list of the background processes that are running in the current shell. So if you're running in a current shell, a bash shell, user administrator, and you want to know all the background processes that are running for your shell, you could use the jobs command for that. Okay, foreground command, FG, common command that's used to run a background process in the foreground. Every now and then you might want to run a background process, but you want to run it in the foreground for whatever reason. So this is a way to kind of do that in a way. You take the background process, shift it into the foreground. The opposite of that is if you want to run a foreground process in the background, you use the background command and it shifts the processes the other way, the foreground into the background. Process priorities. As we mentioned, Linux is a multi-user, multitasking operating system, which means it's what they used to call a time-sharing system, TSS, time-sharing system. And the CPU, although it looks like it's running only your process, it's actually sharing its time with other users running other processes. And it does that by slicing out little slices of time. A time slice is the amount of time that a process is given on a CPU at a particular moment on time. It is used in a multi-processing operating system. In this context, multi-processing means multi-user, multitasking, because it's carrying out multiple processes simultaneously. It's not really simultaneously. It's just very rapidly shifting from one to the other to the other. So it appears to be simultaneous, but it's really not. It's just sharing time slices really, really fast. The more time slices a process has, the more that it has to execute on the CPU and the faster it will execute. And time slices are usually measured in milliseconds, real quick. Especially today with the new i7s, i9s are out now, and things of that nature. They really go fast. Okay, process priorities. We get a little bit into the numbering system here. And 0, which is sort of the default nice value for new processes. Remember, the nice value is our indirect measure. The higher it goes, the lower the priority, and it goes here from -20 to +19. +19 is the lowest priority, which means it's the least likely to receive time slices, and your priority will be closer to 127, because the priority goes from 0 to 127. Okay, over here at the -20 end, it's the highest priority, or it's most likely to receive time slices, and the actual priority will be closer to 0. So you have nice value, -20 to 19, priority value 0 to 127, with 0 right about in the middle. So that's sort of the relationship between nice value and priority. Processes are started with a nice value of 0 by default. That can easily be changed. On some Linux systems, background processes are given a value of a nice value of 4 by default to lower the chances they will receive time slices. Depending on how your system is set up, you may want to You may want to give higher priority to the application and less to the processes. So that depends on the distro, the Linux system, and what you're using. The nice command can be used by the user to change a process as it is started or after it is started, whatever the user wants. Okay, a renice command. Renice command is used to alter the nice value of a process currently running. So you use the nice value to change the value as it is started. If you want to change the value after it's running, there's this renice command right here. And what you could do is, if the process has been running for a while or whatever, you want to change it, you change it using the renice command. As with the nice command, only the root user may change the nice value to a negative value using the renice command. So in other words, if you're an ordinary user, you could change it in the positive range, but you can't go below 0. If you want to change it to negative, you have to be root, or you have to use the sudo command to get temporary root privileges and provide your sudo password. Scheduling commands. This is a very interesting topic because Linux is very, very powerful in that it actually lets you schedule different commands to happen at different times of the day. Okay, at the daemon right here, this ATD, the system daemon that executes tasks at a future time. And it's configured with the AT command. You could remember that by at time. And then there's the cron daemon, crond. You could remember that is cron for chronological, chronograph. Cron meaning clock, time, something along those lines. And this is a system daemon that executes tasks repetitively, in the future. I use this on my systems in that every night at 11:30, my system will automatically scan my hard drive, find any files with a date and time stamp of that particular day, which means the file was accessed or modified that current day, and it'll back it up to an external hard drive for backup purposes. So you could use that for backups, you could use it for security, you could use it for a lot of things. And you can configure that in Linux using what's called cron tables. Okay, scheduling commands with the ATD command. Okay, the AT is used to schedule commands and tasks to run at a preset time in the future. They give different formats here. 10:15 p.m. Okay, AT 10:15 p.m. We'll schedule it to run at 10:15 on the current date. This is a one-time shot. Okay, for today. AT 1050 July 15th will run it at 10:15 on the date specified. July 15th here and here. This is another one-time shot. At midnight, it'll run it again, one-time shot at the current date. Noon, another one-time shot on the current date at noon. And at tea time, for those that have British connections, what's tea time? I guess tea time is 4 p.m. on the current date. So that's a quick preview as to the AT command. Okay, if you're going to use the AT command a little more sophisticated, okay, you could use AT tomorrow, which will run it at the same time that you are, but the next day. So tomorrow, the next day. Okay, AT now plus 5 minutes. Okay, basically you're talking about a time delay. Okay, AT now, but then you're adding your time offset to it, and you could specify hours, days, weeks, or in a batch if you want to run it immediately. Or you could even put in multiple commands, and you can specify, January 3rd, whatever year. So this is a very powerful command in that by specifying when you want it to run, you could run it at almost any point in time you want. Okay, scheduling commands with the AT command. Okay, again, all our configuration files are in the etc directory. So since basically the AT timetables are a form of a configuration file, they're going to be in the etc directory as well. And if you give that an allow permission type of a command, that file listing, all users who can use the AT command will be allowed to use that. If you want to deny users access, you would use the at.deny command, and that will lock people out of using the AT command. But again, you notice you're putting it in the etc subfolder. Scheduling commands with crond is a very similar thing. We sometimes call them cron jobs or chronological jobs. Okay, this is using what they call the cron daemon, which is another type of a scheduler. And what you do then is you use the cron tables or the system cron tables. They're made up of 6 fields separated by a space or tab characters. And we'll take a little bit of a closer look at that. Okay, you see 1 would be the past hour, 2 is an hour, 3 day of month, 4 month of year, 5 day of week. So by specifying these commands, you could specify the day using one of these numbers. That's the basic format you would use. And by using different combinations of this format, again, you could get pretty much any format you want out of it. So let's say you want this my script to run. Okay, the cron table entry would be 20, 40 in field 1, 17. Then you have a couple of asterisks, and then 1 through 5, because you basically want to run it on weekdays here. So that's what your cron table entry would look like. So these are the parameters of when to run it. This would be the command you're actually running right here. Excuse me again. Scheduling cron commands with crond. Okay, the actual spools, as you know, like the printer spool, like any spool, that's a variable. So that, unlike the configuration files, is going to be in the VIR subfolder, because in Linux, the VIR subfolder is your variable folder. This is always getting new things added to it, new processes added to it, and as processes finish, they subtract from it. But this is where the cron tables actually are, because they're variable. Okay, the configuration, okay, the system cron tables, they're in the etc. Okay, they're actually more configuration type of files. User cron table, similar to the AT, there's a cron.allow, and that contains a listing of all the users who can use the cron command, and cron.deny is a listing of all the users who cannot use the cron command. The cron tab command is the command used to view or edit the user cron tables. So cron tab lets you actually look at the tables and possibly edit them. The system cron table. Okay, most Linux systems are typically scheduled to run many commands during non-business hours. This is, of course, to save resources. A lot of end users aren't on the system, and a lot of times late at night, I have my system do it at 11:30 because by then I'm usually not on anymore. I don't want to run it earlier because I wanted to get everything done for that day. If I do something at night, I want it backed up. But if I wait much longer, it'll be into the next day. So that's why I pick 11:30. But Linux systems do a lot of things during non-business hours, and a lot of companies, they like to run things between 1 in the morning and 5 in the morning because their resources are being used less during that time period. So these commands are used to perform system maintenance, system backup, or run very CPU intensive programs. A lot of places that used to dial numbers, they used to do that at night because phone rates were lower. Now with email, that's not as common, but still a lot of bulk email takes place late at night and things of that nature. Most of these commands are scheduled by the cron daemon from entries into the system cron table using this etc cron table right here. And again, this cron table is in the etc subdirectory. So just looking back and summarizing some of what we discussed, I know it was a lot of material. This is a long video, but it's worth it because Linux and most operating systems are based on processes, and the Linux processes kind of define what Linux is by the way they work together. Processes are programs that are actually executing on the system. That's what makes them different from programs which are stored, ready to run. User processes are run in the same terminal as the user who has executed them, whereas daemon processes are system processes that do not run on a terminal. Every process except init is different. That's the exception to the rule. But every other process as a parent process associated with it, optimally several child processes. That's where we get that nice tree structure. Process information is stored in the /proc for procedure file system. So the process information is in proc, configuration is etc, and whatever's variable that's going on is stored in var. That's just basic Linux, the way the file system's organized. Zombie processes and rogue processes, they're together here. They exist for long periods of time and use up system resources and should be killed to improve system performance. Remember, however, rogue processes go overboard and use a ton of system resources. Zombie, not quite so much. You may send kill signals using the kill, kill all, and top commands. Those are the three ways to kill, and there's different levels of kill. 1, 2, 3, 15, and then 9. And we discussed what those were. The bash shell forks a subshell to execute most commands. So most commands you fork and then you come back. And processes may be run in the background by appending and ampersand to the command name. The priority of a process may be affected indirectly, again, indirectly by altering its nice value, and commands may be scheduled to run at a later time using the AT and the cron daemons. So that basically is a summary of what we have. And